All right. So with our acids, we have strong acids and we have weak acids. Today is all about weak acids and what happens, what occurs with these particular acids. Now, with weak acids, we put this in notes a couple times. It says only partially ionized. Great, fantastic. The question I have for you is, okay, if I told you, or I gave you an acid, I said this is an acid, determine if it's weak or strong, and it's almost overly simple. How would you know if something's strong versus weak?
pH.
The pH could be an indicator, but more simple than that, if it's not the list of 7 strong acids and it's still an acid, it's weak. All right. So unless it's one of those 7 strong acids, everything else is weak. And remember, an acid donates or gives away its H plus ion. Okay. So just some general things to remember there. Now, if I gave you an equation, it's really easy to determine if something is a strong or weak acid because strong, one arrow going one direction. Weak, there are 2 arrows going forward in the reverse directions, known as equilibrium. If it's, in this case here, we have a weak acid here, and this is our generic weak acid. We are at equilibrium, which means we can develop or we can write down our equilibrium constant expression. And so remember, from the equilibrium unit, we would say K equals, and what goes on top of our K? What is it? Products. Now, again, this is a generic example here, but you would have H3O plus, which will often just get called H plus, or our hydronium ion. That's what we refer to that as. And then times our A to the minus there, all divided by, there's only one thing on bottom, the reactants. What one thing would it be?
HA.
HA. Why do we not include H2O?
Because liquid.
Very good. Okay. Now, the other thing with us, we are going to consider solutions to be aqueous solutions. Okay. That means water is going to be involved in the process. For an acid, water is going to be that other reactant. Now, it's still a liquid, so it's not included in our equilibrium expression. And then we add one extra thing here, and that's this. Because this is K, the acid dissociation constant, for an acid, we specifically call this Ka. All right? Now, with this in mind, and I kick off these notes like this, I want you to get in the mindset, weak acid, got to use equilibrium, have to use those concepts that we've taught you in those equilibrium problems before. Any questions? Anybody need this? All right, so let's talk about what K is and what can we do with it, okay? And so the K is our acid dissociation constant, and we put that little a to say, hey, this is the acid A for acid dissociation constant. Large K, we said before, products dominate. Large K for us, we have a really strong acid, okay? A lot of H's break apart to form that H3O plus. Small k means very, very little broke apart, means for us weak, okay? Questions on this? Anybody need it?
Yep.
All right, so now we have this, okay? We have a problem. So number one, besides the fact that it says, hey, you're going to use Ka and that's weak acid stuff, if I just gave you the problem and said, hey, go calculate the Ka for this particular problem, how would we know that formic acid was in fact weak? Not on the list, all right? It's as simple as that. Now, what I like to do, not on the list, means, hey, our expression, we have to put in equilibrium. Two-sided arrow, forward and reverse reactions, okay? So here's what we do, and here's our generic setup. that's going to be applied to our specific instance here. Okay, I will admit, kind of a little precursor, you're gonna have to do an ice chart. So give a little gap here on that left-hand side. And we go through this. Let's use blue. Okay, we start out with formic acid. I'm gonna give a little gap on the left-hand margin. And we have HCOOH, and it is AQ. Okay, and again, because it's aqueous, it is combined with water, so we say plus H2O as a liquid. It's weak, so we're at our equilibrium arrows, forward and reverse arrow. And then this H from formic acid, this H right here, I'm just going to put the yellow line over it, gets donated to H2O. And so as a result, our products is going to be H3O plus, which is AQ, and our particular formate ion, which looks like this, HCOO with a minus, and we have an AQ. Now, I'm going to tell you right now, this is already balanced, which this is why I like acid-base equilibria better than equilibria, because most of the time, not always, but about 95% of the time, one coefficients across the board, which makes life a lot easier. But because we are at equilibrium, we're going to have to develop our ice charts. So I'm going to automatically go ahead and put this as our ice charts here. And so we're going to have I for initial, C for change, and then E for equilibrium. And in our problem, unfortunately, we are only given one initial value. That one initial value that we are given is this 0.10 molar formic acid, right? So 0.10 big M. It doesn't really matter that we have H2O or not, because we're not going to include it in our big K expression, so I skip it. And I don't mention anything about H3O plus or CHOO minus. Because I don't mention that, yeah, there we go. We can assume that these are going to start out as 0. Now you're sitting here thinking, okay, wow, not a whole lot of info. I don't even know my K. What can we do? Well, if we take a look back on our other piece of information, our numerical value here, we are given the pH at 25 degrees Celsius. Now, pH we can do something with, okay? What was our formula that we learned from day 2 notes?
Log of H plus or slash H3O.
Yep. I'm going to write this down in purple here, and I am going to say exactly that here. I am going to, and I'm going to write this in the bottom right-hand corner. I'm going to say, okay, our pH is equal to the negative log of the concentration of H3O plus. Okay, well, I'm just going to go ahead and plug in my value for pH, which is 2.38 equals negative log of my H3O plus. Okay, now, is anybody opposed to me just go ahead and calculate it?
No.
The key thing with this that I've seen mistakes be made is, remember, this is negative log. So yesterday we took and we divided everything by -1 to make this number out here, the 2.38, actually negative. And so we would do this. We would say second log, which gets us 10 to the x, okay? We would put in -2.38. I'd close my parentheses. I get this decimal number. I would rather use scientific notation. And I'm also only going to use our 2 sig figs because of this 0.10. And so when I do this, my concentration of H3O plus is 4.2 times 10 to the negative third. And remember, those brackets indicate, hey, concentration. Now, this is the H3O plus concentration at equilibrium, okay? At equilibrium. So I'm going to go ahead at the equilibrium value, copy and paste this right here, and I'm going to say this, 4.2 times 10 to the negative third m, and we're just going to think about this for a moment. If we started at 0 and ended at this 4.2 times 10 to the negative third, what did we do?
Add
We-
4.2 times 10 to the negative.
Yeah, we added that amount. Now, because we know the change, a numerical value for the change, we can use stoichiometry. All right. Again, everything is a 1-to-1-to-1 ratio.
So it's all the same.
It's all the same. So my question is this: we go from 0. Do we add or subtract that number?
Subtract.
Can we get negative?
I mean, now.
We add, right? So we say, all right, this formate ion, we also have to add 4.2 times 10 to the negative third, and we end up with an equilibrium value of 4.2 times 10 to the negative third. And so if we added on our right-hand side,
Subtract.
yeah, we got to subtract on our left-hand side. So we have 4.2 times 10 to the negative third m. And so on our calculators, we'd say 0.1 minus 4.2 times 10 to the negative third. And I get a value. I'm going to keep that 2 sig fig train going here. In my calculator, I get 9.58 times 10 to the negative second. 2 sig figs would get us 9.6 times 10 to the negative second m. All right, now we're in the driver's seat here because we have values, we have numbers all at equilibrium, okay? What we need to think about now is we need to think about K. And I'm going to rewrite this just so you can see it. And so with our K, remember it's Ka because we have an acid, okay? Our products in this case is going to be H3O plus times the formate ion HCOO minus, all divided by that formic acid concentration. And I'm going to say this before I start inserting numbers in solving for our exact Ka. Remember, the values you put in your equilibrium expression have to be at equilibrium, okay? So I'm going to start, and I'm going to switch to my purple numbers here that I put in. And so my H3O plus concentration is 4.2 times 10 to the negative third times that same exact number, which if you want to square it in your calculator, that is perfectly fine. So 4.2 times 10 to the negative third, all divided by the equilibrium concentration of formic acid, which is 9.6 times 10 to the negative second. And when we plug 4.2 times 10 to the negative third times 4.2 times 10 to the negative third, all divided by 9.6 times 10 to the negative second, what do we get? And let's round to 2 sig figs here for our Ka.
1.8 times 10 to the negative 4.
Yep, 1.8 times 10 to the negative fourth. Remember, Ka has no unit, so we would leave that exactly how we have it here. Key things. 1, we are given a pH. That allows us to calculate an equilibrium value. We can find the change, and we go from one side to the other via change using stoichiometry. Okay? And any questions?
No.
All right. So let's try another one. Oh, you're not. Perfect. All right, so now we transfer problems here, and we have a little bit of an extension, percent ionization. I said this yesterday verbally, but I have not expanded upon this, okay? Weak acids, or weak bases for that matter, dissociate less than 5% in general. Not everybody does, but in general, only 5% or less break apart from that original acid or base and become ionized. Okay, so here we go on this. Same problem here. I used our numbers that we found from our info, and so we're just going to plug some numbers in. Okay, this is again a copy and paste the problem. You want to see how much actually became that acid, or how much actually broke apart from our particular acid there. So percent ionization. All we're going to do here is this. Our percent ionization, I'm just going to say percent I is equal to the amount of H plus that's ionized. So we have 4.2 times 10 to the negative third, all divided by the original acid concentration, which was 0.10. And then we, because it's a percent, multiply by 100. Okay? And so when we do this, we just take 4.2 times 10 to the negative third divided by 0.1 times 100. And what's our percent ionization become?
4.2.
Yep, 4.2% ionized. Okay, now in general, the percent ionization of a weak acid is going to be less than 5%. Okay, questions? Does anybody need this? All right, so now we try a little bit of a different problem here. Okay, I give you very, very little information. I want you at the end of the day to calculate our pH of HCN. Okay, now HCN, yes, we're doing weak acid notes, but if I just gave you this problem, how would you know that it's weak?
It's not in the thing.
Too easy. Not on the list, right? Not one of the 7. That means it's weak. Because we can give away that H, that means it is our acid. Okay, so we're going to start with HCN. Okay, again, give yourself a little room on the left-hand side because we're going to need it there. But we have HCN. It's an aqueous solution, which means we have to react it with what?
Liquid.
Liquid water. Yep, H2O as a liquid. It's weak, so we draw our equilibrium arrows. Now, our H from hydrocyanic acid gets donated to the H2O, and it's going to form H3O plus AQ plus, we're going to end up with our cyanide ion. Okay, again, nice part about acids and bases, all 1-to-1-to-1 coefficients. Very rarely do we see something other than ones. Now, it's equilibrium, so we got to go ahead and we got to draw our ice chart. So we're going to say I, C, and E. Okay, we're only given one value. What value are we given?
0.20.
Yep, of that HCN, 0.20 big M. Nothing else are we given. So what can we assume about the H3O and the C?
0.00.
Okay. Now,
It's actually 0.
we need a little extra help here with what we're going to do now. So these Ka values, you don't have to memorize them, obviously. Ka are really, really helpful to have on hand. Where'd you get this? So you can look for HCN. We're going to use it here in just a second, but I want to get our mindset correct, and I want to think about our particular equilibrium expression. And again, just like an equilibrium, I always like to start out, and I like to have some basic where I write out the K. So remember, it's Ka for an acid. Products is going to be H3O plus times our Cn minus, all divided by HCN. Okay? Again, that's what I more or less call our formula that we can utilize at the end. But here is what I want you to look up. On that chart, if you find HCN, there should be a value for that HCN.
4.9 times 10 to the negative 10.
Good. 4.9 times 10 to the negative 10. This is going to become very, very useful as we solve this particular problem. Okay? 4.9 times 10 to the negative 10. Good info, again, to come back to. Now, let's think about this. We got to figure out the change. We don't know it. In math class, what do we do if we don't know? Yeah, we go ahead and say x. Well, if we start out with something, we have to subtract that x. Okay, if we start with 0, we have to add something. We can't have negative concentrations. So we're going to say plus x and plus x. Okay, so equilibrium. When we get down to our equilibrium values, I'll put them in pink here, we would end up with 0.20 big M minus x. 0 plus x is x, and x. All right? Now, if you can kind of see where this is going,
Quadratic.
yeah, I like to avoid that at all possible cost. And so what we can do, I'm going to write this in the lower right-hand corner, is we can make an assumption. Okay, I'm going to write the assumption here in red. All right, so I'm going to call this right here our assumption. And our assumption is this. If we take our Ka value times 100, and it is smaller than our concentration, in this case of our acid, which is HCN, then we can assume that the 0.20 molar minus x is such a minute difference that essentially 0.2 minus x would just be 0.2 molar. Okay, so let's try this out. We're going to take our Ka value. We're going to take our Ka value that is given in our chart and that we wrote down in this problem, and we're going to say this, okay? We're going to say, and I'm going to write it out to the left a little bit, 4.9 times 10 to the negative 10th times 100, and we'll go ahead and do that. That is going to equal 4.9 times 10 to the negative 8th, okay? Is this value right here that we just wrote down, is that bigger or smaller, does this hold true, than our original value of our 0.2 molar?
Smaller.
Yeah, so check this is true, which is really, really nice. Makes everybody happy, right? What this means is this. We backtrack, and at equilibrium, we don't have to say 0.2 minus x. We can say okay, this change would be so small that at equilibrium for our HCN, we are in fact just going to use 0.2 as our molar, and we're going to save us a lot of time and effort. So here we go. We still need to find the pH, which we're a little ways from that, not too far away. But here we go on this, okay? RKA, I'm going to write in pink, is going to start out, and we're going to copy and paste this number. So we're going to say 4.9 times 10 to the negative 10th equals X times X, all divided by, remember, we can just use 0.20 molar. We don't have to worry about the minus X. This is going to consolidate to 4.9 times 10 to the negative 10th equals X squared, all divided by 0.2 molar. And are you all right if I just tell you what X is? Okay. All right, so if we solve this, I'm going to take 4.9 times 10 to the negative 10th times 0.2. I'm going to take that number and I'm going to get the square root of what I just got there. And my X is going to equal, I'm going to write this below here, my X is going to equal 9.9 times 10 to the negative 6. Now, we still need to find the pH. Well, check this out. X is equal to the concentration of H3O plus. Okay? So if X is equal to this value right here, what formula can we plug that value in to find the pH? Too easy, all right? So then our last step here, all we need to do is plug this into our pH formula. And so remember, I'm going to write this down just so you have it. The pH is equal to the negative log of the concentration of H3O plus. So we're going to plug this number in and we're going to say, okay, the pH is equal to the negative log of our 9.9 times 10 to the negative 6. And so if we plug that in here, we say negative log 9.9 times 10 to the negative 6. Close that parenthesis. Our pH equals exactly 5.0. Okay. Now, this is nice. We avoided the quadratic because this assumption worked. Make sure you check if the assumption works. I would like to say yes, it works every time, but that's not always the case. Some of those Ka values are actually very close to 1. Okay, questions? Anybody need this? All right, let's do this. All right, let's write these steps down here, and then let's talk about polyprotic acids, and we will save the polyprotic example for a different day. Okay, so using Ka to determine pH. Again, 1, recognize you have a weak acid. 2, once you have a weak acid, use our equilibrium constants or our acid equilibrium constant, the chart, to find our Ka. Again, I always like to write down the expression because at the end of the day, it kind of gives us a formula to fall back on once we get our equilibrium values. Okay? We'll probably only be given one value, which is our initial value of acid, and then you have to go and you have to find all the equilibrium values. Check that assumption. That's the only thing that's not on these steps, but check that assumptions. So if your Ka times 100 is smaller than your original acid concentration, the assumption works and we avoid the quadratic. If not, you got to use the quadratic to solve for X and solve for H+. So questions? Anybody need this?
Can you just do quadratic even if if you want to do quadratic, you can do it.
Yes, you can do quadratic if you want to. You may end up with a very slightly different number, but it's not going to affect the pH drastically. Like we may have solved the last problem as our with the quadratic, and we may have got a pH of like 5.01. In reality, and relative scales, 5.0 was 5.01 pH. But yes, you can. You at the end of the day, you would still have gotten x equals 9.9 times 10 to the negative 6. All right, last thing that I want to leave us with today is this polyprotic acid. Poly means many, protic is that H plus. Guess what? Sulfurous acid, H2, has two H's to give away or donate. What happens is essentially two acid-base problems occur back to back. They're both weak, that's why I chose sulfurous acid, and they have two Ks. The first one with H2SO3 is referred to Ka1. The second one, where HSO3 minus gives away its next H, is Ka2. Okay, so we will solve the final parts of this problem here. Questions?